Okay. Uh, my name is Soka King, and I'm from Maxwell Lab. Now I'm the second year master student, and the and today I would like to share this paper. The title is "The Surprising Effectiveness of Test and Training for Abstract Reasoning." So this is the information of this paper. The author is from the MIT. And this is the abstract of this paper. The researchers temporarily updated model parameter using loss function derived from input data during the reasoning process and validated the effectiveness of test and training in improving LLM reasoning capability on the ARC benchmark, and they systematically analyze the critical components required for applying test and training on ARC tasks and propose a novel TTT data generation method and a self-consistency component. The final result demonstrates that the large model equipped with TTT could rival or even surpass the performance of many symbolic reasoning-based models on ARC. And let me have a brief introduction of test and training. And after the release of O1, the importance of using additional test and computation to enhance large model decoding performance has become increasingly evident. Such methods including like chain of thought prompting, measuring voting, code execution, and search, among others. Recently, another widely discussed extensive strategy is test and training. And test and training was initially introduced by researchers from UC Berkeley and UCSD in 2020 for visual models and later applied to sequence model in 2022. TTT updates model parameter explicitly through gradient steps based on test and input. Unlike standard fine-tuning, the test and training can operate under extremely low data conditions, typically through unsupervised learning on a single input or supervised learning with one or two label examples in context. So how is test and training defined? According to this paper, the test and training involves dynamic parameter updates during inference for adaptation, which remain relatively underexplored in the era of large models. Simply put, like test and training is a form of transfer learning, where the model leverages the structure of test data to improve predictions. And the MIT researcher described test and training as a process of adjusting the model itself during test. And the general working principle for test and training is as follows. First, starting with the initial model parameter theta zero for each test input, and training dataset T is first generated from the test input. Then the parameters are optimized to minimize the loss function L, producing temporarily updated parameter theta D for prediction. And after generating the prediction, the model reverts to the original parameter theta zero to process the next instance or the next batch. And because the design space for the test and training method is vast, however, current understanding of which design choices are most effective for large models, especially in learning new tasks, remain limited. And to address this, the MIT team systematically studied the impact of various test and training design choices and their interaction with pre-training and sampling strategy in this paper. And during this process, they identified several key elements for the effective application of TTT in future learning. And this key element is first performing initial fine-tuning or on similar synthetic tasks encountered during testing. Second, using an enhanced leave one out task generation strategy to contrast test and dataset. Third, training per instance adapters. And the last is self-consistency under reversible transformations. And through this careful selection of this component, as discussed earlier, the test and training significantly improved large model performance on the ARC benchmark. And the result demonstrates that the task previously solvable only via program synthesis can now be addressed using purely neural network approaches with the TDT framework. This finding challenged the assumption that symbolic components are absolutely necessary for solving such complex data. And let me give a brief introduction of the ARC challenge. The ARC benchmark is the full name is the Abstraction and Reasoning Corpus Test Dataset. And this dataset And this dataset is designed to test abstract reasoning abilities through solving visual puzzles. Each task consists of 2 degrees with shapes or patterns involving up to 10 colors and created using shared transformation rules. The goal is to predict the Y test for X test by reasoning about transformations. And the 2 approaches to solve this task on the ARC benchmark the first one is about program synthesis method. It's about to discover the transformation function f and apply it to the task examples. And the second one is about fully neural method. It's like to predict output y and without explicitly modifying the function f. And in this paper, the researcher used the second method, the fully neural method. And so what dataset and loss function during the TTT? The first part, it's about data generation. Like given a task, the input-output pairs are transformed into an augmented test and training task set D. And the researcher achieves the task set through a 2-step process. The first one is about creating a leave one out in context learning task set by excluding the J's input-output pair from the training examples. Like you can see in this picture, the test task is include the x0 to x3, and in the step 1, the leave one out task, they exclude the x3, and then go into the step 2, the process by applying reversible rule-based transformation to this set to obtain an augmented dataset. It's about like researchers select simple transformation such as rotation, flipping, swapping, scaling, identity, and then finally they get a test and training dataset. And also there is another approach about end-to-end approach. To compare with the above test and in-context learning approach, the researcher also evaluates the end-to-end learning method. In this approach, each input-output pair is treated as an independent training instance, directly creating a supervised dataset from the demonstration. And notably, this is equivalent to the leave n-1 out task set in ICL, except no training example are provided as context. And the next part, it's about the optimization objective. During the TTT, the research used LoRa to optimize task-specific parameter while freezing most of the base model. This approach retains the general capability of the model while enabling efficient adaptation computations. As shown in the figure, the figure is in the next slide. The TDD method increased the accuracy of fine-tuned model by 6 times, like from 5 to 29. Additionally, the ICL task significantly outperformed end-to-end tasks. And under identical conditions, the end-to-end approach shows an 11 relatively performance drop. So what inference strategy after TTT? The first part is about the enhanced inference. The ARC dataset lack chain of thought reasoning, making it majority voting infeasible for improving inference. So the researcher adopt an approach similar to TDT. It's like creating a small set of tasks and applying reversible transformation to generate multiple variation for the origin task input. The researcher proposed an enhanced inference strategy, generating multiple prediction candidates using geometric transformation combined with greedy decoding. And for a given task, which includes training example and task input, they use the reversible geometric transformation to create equivalent transformed version for the task. And this process is very similar to the process of generate TDT dataset that I mentioned above. And the second part, it's about integrated prediction, the voting strategy. This method involves a two-stage voting process to gradually narrow down the best candidates. The first part, it's about intra-transformation voting. The predictions are grouped by transformation type T, and within each group, the top three predictions within the highest frequency are selected. The second part is global voting. The candidates selected in the first stage are subjected to global voting. The top two predictions with the highest overall frequency are chosen as the final result. And in case of a tie, prediction from the identity transformation are given priority. And as shown in this figure, using individual transformation types generally result in poor performance, with the transpose transformation having the lowest accuracy. But however, aggregating these transformation results through the voting procedure significantly improve in performance. And moreover, using self-consistency voting for aggregation is consistently beneficial, aligning with prior research findings. Additionally, flattened voting improves accuracy, but hierarchical voting procedure perform even better, surpassing the former. So what fine-tuning before TDD is needed? The first is about using existing generator. The research used the REARC generator function to create additional example for the task. The second part is like they use few-shot prompting with large model to generate more data. To create new task generator, they use few-shot prompting with example from existing dataset, and they put this example into the large model and add some task description like categories, summaries, etc. They added this description to enhance the generator. And the third part, it's about geometric transformation. It's just like the same as above. The transformation were applied to inputs and outputs, or both, and generating more diverse training data. And what about the impact of fine-tuning data on the test time training performance? The research compared model fine-tuning on different datasets in the figure. The result revealed that the model trained with REARC and the rule-based augmentation performed best. Surprisingly, the task generated by a large model led to a 5% performance drop. I think maybe the reason is because the current large model-based task generation method may require more sophisticated filtering mechanism. And finally, they found that the fine-tuning performance showed almost have no correlation with the test and training performance. And the model size, about the model size and the test and training scaling. The figure also presents the results for different model size, like increasing the model size continuously improved the fine-tuning performance, with the 8B model achieving the highest accuracy of 36%. And furthermore, the test and training effectively bridged the performance gap for smaller models. Like for the 1B model, only applied fine-tune, they only have 5%, and for the 3B model, if only applied on fine-tuning, they only have the accuracy of 11%. But if we add the test and training to fine-tuning together, for the 1B model, they can achieve the accuracy to 29. And also for the 3B model, it can also achieve 29. So after applying test and training method, the 1B and 3B model achieve similarly accuracy levels. So what about the limitation of the test and training method? The first, it's about the high computational cost. And the second, it's limited statistical analysis due to the computational constraints. So it's all about the high computational cost. And like for the future work, how to further doing something on the test and training. The first one is about optimizing augmentation strategy, because in this paper, the researcher only applied the geometric augmentation strategy. Maybe there is more other strategies to optimizing. And the second is about exploring broader application of test and training. So this work demonstrates that test and training can significantly enhance the performance of large models on the widely used ARC dataset. Learning task-specific LoRa adapter and generating augmented test and datasets through geometric transformation are critical. Additionally, the researcher developed an enhanced inference pipeline that generates multiple predictions using reversible transformation and selects the best candidate through self-consistency. The overall pipeline applied various test and computational methods, with each component contributing positively. This finding indicates that not only can test time computation improve LM performance, but different test time methods can also complement each other. The new test and training pipeline, combined with existing method, achieves sort of our result on the ARC public set, matching the human average performance of 60%. In summary, the test time methods are likely to play a crucial role in advancing the development of the next generation of LLMs. Thank you, and that's all.
ありがとうございました。ご質問がある方はお願いします。大丈夫ですか？ 父さん、発表ありがとうございました。
Okay, thank you.